Welcome back. We are again in one of the videos related to induction and recursion, and we'll be looking here at mathematical induction and algorithms. Now we're going to see how we can apply the mathematical induction principle on an algorithm. Now, what are we going to consider? We are looking at the different types of algorithms, and here we will take an example where we look at a greedy algorithm, which is called the scheduling algorithm. Now, mathematical induction is very important for the study of algorithms because we have to prove that once we have described an algorithm, that algorithm is true in all circumstances. So we have to be sure that once we start using an algorithm, that we can say that the algorithm is correct, whatever the input values are. Now, we have to be sure of that, and mathematical induction will help us. We cannot use mathematical induction to create algorithms, but it's very useful to prove that an algorithm is correct or not. We can also find out that when we do the mathematical induction that there is an error, so we identify that something is wrong. We can, in fact, either cancel the algorithm or adjust it, correct the algorithm, and of course, we also have to see, we have to be sure when we start using an algorithm that algorithm is, of course, universally applicable. Now we consider a scheduling algorithm. I already mentioned it. We have an auditorium where we are organizing speeches, and each talk or speech is characterized by a start time, st index j, and an end time et index j. Basically what we say that is that no lecture can start at the same time, but the next lecture can start when the previous one ends. So basically we can only have one lecture at the same time, and we can start a new lecture anytime after the end of the previous lecture. So there is no really a pause in it. We just can put them one after the other back to back. Now let's have a look at those elements. So what we're going to do is that we are going to order the different lectures in a non-decreasing set of their end times. And ET1 is the first ending time, ET2 the second, and so on. So we look at the end times of the different talks or presentations that we want to schedule. Now, the greedy algorithm here is always taking the obvious solution, like we've seen in greedy algorithms before. The greedy algorithm takes the next best possibility. A greedy algorithm doesn't always give an optimal solution. An optimal solution in our case of the talks would be that we have the most talks possible in the auditorium. Now what we have to prove here is that with this greedy algorithm, that it actually leads to an optimal solution. So let's have a look at it. Let's prove the task scheduling algorithm. First, we have to look at the basis step. The basis step means that the greedy algorithm managed to plan only one talk 1, with the start time st index 1 and et index 1. So it means that there is no other talk that can start at or after end time. When we look at the list of the non-decreasing order of talks, we added talk 1, and the other remaining talks in the list start either before the end time of 1 or after the end time of 1, and only one talk could be selected which concludes the basis step. So we can only select one, other activities, other talks cannot be selected because it is not possible to add them to the auditorium. The second step that we have is the inductive step. And with the inductive step, or when we look at the inductive hypothesis, this says that when P of k is true with k an arbitrary integer, that the algorithm always schedules the most possible tasks or talks. We must show that under the assumption that P of k is true, that P of k plus 1 is also true, and that the greedy algorithm always schedules the most talks possible. Say that k plus 1 talks have been selected by the greedy algorithm. Based on this, we can say is that we see is talk 1 with the earliest end time is part of the schedule, because this is the talk with the earliest end time, and basically this talk should be first in the set of talks. From now on, we schedule as many as possible talks that begin at or after the end time of talk 1. And basically, we see that the algorithm, the greedy algorithm, schedules k talks because we had k plus 1. Talk 1 is the first one, so we still have to schedule k talks. We can apply the inductive hypothesis to conclude that it has scheduled the most possible talks k plus 1, so P of k plus 1 is true. Basically, this proof shows that the task scheduling algorithm that we've determined, that we developed, is a greedy algorithm, but on the other hand, it also provides us the most optimal solution. So basically we can say, since the basis and the inductive steps are true, that the task scheduling algorithm P of n is also true. So this was an example how we can use in mathematical induction to prove algorithms. There are much more proofs available. We will prove that also later in the course of algorithms, because we have to be sure that when we find an algorithm that it complies, that it's correct. And in the next presentation, we will look at some creative uses of mathematical induction, because there are all kinds of elements, statements that we can prove. You're doing a great job, and I'm looking forward to see you in our next session. Thank you, and bye-bye.